problem. One catalog is 1,000 times denser than the other. It's a very bad place. No, it's not as simple. Everyone thought it was easy. Maybe
Because
there are
I
places
thought
where it's easy.
Maybe you can explain what Chask is.
Simple, really.
Oh.
Already.
All right, I will explain. There's a story behind it.
Too many acronyms,
Too many
much
acronyms.
jargon. Can't keep up with it.
But this one is easy to remember. It's easier. It's easy to remember. So, so are we on? So is the video on? And you can hear me from this? You can hear me from this? Okay. Thank you. Okay, so I suppose I should introduce myself first. I am Vinay, and through a process which I don't entirely understand, I'm giving this talk instead of Eric. I think I asked Eric for 10 minutes to talk about upper limits, and then he said, "Why don't you also talk about Poisson processes?" And it sort of grew from there, and now he's resting his voice while I'm telling you stuff about all these things. So I am actually I'm from the CFA, of course, but also part of this Chask AstroStatistics collaboration. And Chask actually currently stands for the Chask AstroStatistics Collaboration. It started out as the Chandra AstroStatistics Cabal. It became the California-Harvard AstroStatistics Collaboration. And then Harvard objected to our taking their name in vain. So now it is just the Chask AstroStatistics Collaboration. So that's, what can you do? Actually, now I should say it should be ICHASC because it's the International Chask AstroStatistics Collaboration. So this is basically the plan of action that things that I want to cover. Most of this is going to be pretty obvious to most of you, but I think it's useful to have this sequence down in there as a way to get to the rest of it. This is where I really want to get to. So basically, I'll start with talking about the Poisson likelihood, and then a brief introduction to Bayesian analysis. I'm not a Bayesian. My philosophy is basically anything that works. However, we will talk about when we talk about uncertainties and things like that. You will see why I prefer to do things from a Bayesian point of view because frequentist confidence intervals are very difficult to explain. And if you've seen Frank Primini's email this morning, aperture photometry is one of the things that I'll go through and eventually get to upper limits. So, Poisson likelihood. So, let me just go through a simple derivation of this, how to get to the Poisson likelihood, just so that you get used to seeing the form of the equation. So consider n counts that are uniformly distributed over an interval t, tau, with a constant rate r of n over tau. So there's no complications about flares or any such thing. And you want to ask, you want to know what is the probability of finding k counts in a small interval delta t. And if let's say you pick a randomly selected interval, and you write this factor, the fraction of the coverage rho, and that turns out to be because r is n over tau. That's the expression. And finding k counts in that interval, given that there are a total of n, it's just that the fraction of time that you find these photons in that interval times the fraction that you don't, and there are nck times number of times that you can find this combination. This actually reduces to the Poisson likelihood, the Poisson distribution, which looks like that. It's actually very simple to get from there to there. in fact, just 3 steps. And let me, if you really, I'm sure you all believe me, right? It's very easy. So let me just step through them. So first step, you just expand that out. You write NCK as that factor. Rho is that, and 1 minus rho is that. And then you just flip-flops on a couple of these factors. So you move the n to the k over there, bring the k factorial over here, and you break this n minus k into those two. And now you just consider the case when n is very large and delta t is very small. And what happens is that this thing goes to 1, this thing goes to 0 for a given k. It goes off to, so this factor goes off to 1, and this factor becomes e to the minus r delta t, and that is all you are left with. So that is, this is a standard derivation of how to get the Poisson from the binomial, and essentially the way you read this is the probability of seeing k given that the strength that you expect is r delta t is r delta t to the k or k factorial times e to the minus r delta t. So much for the Poisson likelihood. Let me tell you a little bit about the Bayesian analysis. So briefly, but before I go there, I mean, this is, all of you probably already know this, but it doesn't help to reiterate it. There are 2 major camps in statistics. One is Bayesian and the other is frequentist. The big difference between the two is that in Bayesian analysis, data are sacrosanct. You don't touch the data. It is the model which is considered a variable. In frequentist analysis, it is the other way around. You have one true model parameter values, and you do repeated experiments to get different data sets. So the data are essentially considered are the variables, and generally you get the same answers from both cases, with some exceptions which I will point out later. But Bayesian analysis, by and large, is a calculus for conditional probabilities. And just to orient you, this is a bit of a notation. So we usually say P of something, where the something could be a proposition. So you talk about the probability of a proposition. You talk about the probability of A and B, or A given B, or about probability densities in the form where x is a continuous variable and you look at a functional form. I will switch between point probabilities and densities without warning you often. And actually it turns out it's not such a big problem if I do that. But if you do get confused, please feel free to stop me and ask what's going on. The main things that you got to remember is that these expressions, the probability of A or B is the probability of A plus the probability of B minus the probability of A and B. And the probability of A and B is the probability of A given B times the probability of B. Now if A and B are independent, then this just drops off. It just becomes the probability of A times the probability of B. And from this comes something that's extremely simple and powerful called Bayes' theorem, and that is related to how we just expanded probability of A and B as A given B times B, which could also be done as B given A times A, and those two should be exactly equal, and you set that equality sign, and that's what you write down here. So the probability of A given B is that of B given A times A divided by B. Now you're thinking, okay, this is all very simple, but it can be extremely powerful. So for instance, suppose you take this A and you associate it with model parameters, and you take this B and associate it with data, and suddenly you have a way to figure out how to estimate your model parameter values given the data. And that is what I have written here, where theta is generally there's a statistics jargon issue here, where Data or anything that is observable is usually written as Roman, and anything that is model related is written as a Greek letter. And what is more, previously, this I went from. I mean, I was talking about point probabilities, just points, like flipping a coin, probability of heads, given a unbiased coin or something. Whereas here now, theta could be a continuous variable, and this is written on the real number line. In fact, it could, theta could be multidimensional, and this could be a 100-dimensional space. And it, this is the, you start from that expression, and you have the exact same expression, magic. You are suddenly working at 100 dimensions more, and that's why I say I call it extremely powerful. So let's label these things. So first of all, this thing where you have the probability of data given the model parameters, that is called the likelihood. The thing that is just the model parameters, that is called the prior. This is a normalization which I will ignore from now on. And the thing on the left is called the posterior probability distribution. So you start with your prior, you look at the data, and you get to the an estimate of your the new estimate of your model parameters. Maybe I should say a few things about the priors, right? So this is a very famous quote that is usually attributed to Carl Sagan. Extraordinary claims require extraordinary evidence. I actually tried to find out who said it first, but I could not. So if any of you know, please let me know. But when you see this statement, I mean, the first thing that you should ask is why? Why is it that we are scientists? Everything should matter equally, right? But that if I tell you that an AGN varied in its intensity, you will believe me without a second thought. Whereas if I tell you that I discovered an error in Einstein's 1905 paper, you will not. So it is true, definitely true, that extraordinary claims do require extraordinary evidence. You know this in your gut, and the question is why? And the answer is priors. For some reason, humans seem to think in terms of priors. So again, this is the Bayes theorem, and that factor over there is the prior. And the prior, it's unfairly maligned as subjective, though actually it's just a way of, it's a mechanism to encode your assumptions into the flow of your analysis. And generally, when your data are weak, your analysis is going to be dominated by what your priors are. And when your data are strong, your priors don't really matter. It's often in between, when neither of those things are true is where most of your analysis are. So you do have to think about what the priors are. So the basic idea is always that you update your prior belief with new data using Bayes' theorem. And this is one of the big advantages, I think, that Bayesian analysis has over frequentist, for instance. It lets you daisy chain the analysis in the sense that you start with one analysis, you figure out what the posterior distribution is from that. If you do another observation, you can take the posterior from the previous observation analysis and put that in as a prior and continue on. This can be very, very powerful. Of course, if you try to do that with some sources in the Orion Nebula, you might get wrong answers because the sources vary quite a lot. When your prior is informative, it does take more data to make a larger change. And basically, technically, the biggest difference between likelihood analysis and Bayesian analysis is the prior. It is the prior that converts your likelihood into the posterior probability. So instead of having something that's a function of the data, you can estimate a function that is of the model parameters. And once it's a function of the model parameters, you can do all sorts of tricks like marginalization and profile likelihoods and that sort of thing. So let me give you an example of a prior distribution, and that would be the gamma prior. And just for reference, I put the Poisson distribution over there because the gamma prior is a conjugate prior to the Poisson distribution, which means that it has the same functional form, and it is extremely useful in most cases that we deal with in the Poisson cases. And the form is simply that you have two parameters, alpha and beta, or defined over the non-negative real number line, x, and it's just x to the alpha minus 1, e to the minus beta x, and times some normalization constant. Alpha, it turns out, is if you take the mean of this distribution, alpha is the mean squared over the variance, and beta is mean over the variance. And one of the nice things about this is that as alpha approaches 1 and beta approaches 0, this function flattens out and becomes sort of like a flat non-informative prior over the real number line. Maybe I should say one more thing about this non-informative priors here, which is that there is no such thing as a completely non-informative prior. So for instance, here, for example, this is flat in the real number line, but if you're looking at, for instance, say column densities or something, you're much better off trying to have something that is flat in log space. And choosing one of these things is actually an informative choice. So there are priors that are less informative and more informative, but there is nothing that is truly non-informative. And another advantage of the gamma prior is that for non-trivial alpha and beta, that is alpha not 1 and beta not 0, it acts as a fairly informative prior. If you expect to observe alpha counts in a beta exposure or effective area or something like that, then you can use that as a very nice proxy for the Poisson. Just to show you what they look like, this yellow line over here is 1 over x, just for comparison. And then there are different colored lines or for different values of alpha and beta. And here's the expression just to orient you. And you can estimate the mean as alpha over beta and the variance as alpha over beta square. That works both ways. Okay, and the next thing that about Bayesian analysis that I wanted to talk about was confidence ranges, essentially how you get to an uncertainty in a parameter. It is generally defined by the width of its probability distribution, and this is one place where the Bayesian and frequentist have very different views on how things are reported. So the frequentist case is, they call it a confidence interval, where the intervals are computed at some significance p. They will contain the true value a fraction p of the times the experiment is repeated. In contrast, the Bayesians, they call it the credible range, and for that, the interval at a significance p will contain the true value of the parameter with probability p. I forgot to say that according to the posterior distribution density function. So let's first talk about credible ranges. Okay. First of all, this is something that I have had a lot of questions about, and that is that credible ranges are not unique. They set bounds on the parameters, but as long as whatever the significance that you set, it can go from practically any point to some set value on the other end. There are many types. There are equal tail distributions, intervals, the highest posterior density, Gaussian equivalent sigma, mode specific, and so on. So let's give you a couple of examples. I just crashed these out this morning. I was trying to switch between this and actually scratching in real time, but I decided that would not be a good idea. But anyway, so let's say this is your standard this kind of distribution that you might have. you calculate the mean, which might be over there, and then you calculate the variance, and you calculate a sigma from that. That is what you would call a Gaussian equivalent sigma. So you go plus minus 1 sigma, and you see where those bounds are, and then you can calculate. You can say that's your uncertainty in the model parameter. But as you can see, if there's any skew at all in your distribution, that could be a very bad idea. There is, the typical the idea of a sigma is that you enclose 68% of the mass of the probability distribution within plus minus 1 sigma. That does not necessarily happen. In contrast, you could do this. You could take 16% on this side and 16% on the other side away, and leave whatever is whatever is left as the quote-unquote equal tail interval. The equal tail interval is actually a very nice thing, even though I have illustrated it with a very bad case where it actually excludes the mode, the most probable value of the distribution. The equal tail interval is invariant to transformations, meaning that if you take the log of the parameter after you do this, and you take the log of the interval, it will still be the same equal tail interval. That's not the case for anything else. Here's another one called the highest posterior density interval. So you basically pick something, start from the top, you work your way down until the area under this curve includes the specified probability, the significance. The advantage of this is that it is guaranteed to be the smallest uncertainty that you can put on the parameter. The disadvantage, of course, is that it is not transformation invariant. So it wouldn't. If you're trying to do any relativistic astrophysics measurements, do not use the highest posterior density. It is not. You can't do Lorentz transformations. That's basically what I had said. Okay. So on to the frequentist confidence interval. So you saw the definition before. So the question is, how do you actually get it? So what you actually do is you invert a hypothesis test. You ask, what is the likelihood of the data for different possible parameter values, and then you define a confidence region at some level as those parameters which are not rejected. Okay. So the main advantage of this is that it is very precisely defined, meaning you can always there's only one confidence interval that you get for any given calculation. The disadvantage is understanding what it's doing. So just to give you an example, so when suppose you have a Poisson when there are n counts are observed, you can place an upper bound by looking at all these values, all these cases where k is less than or equal to n, and set that to 1 minus gamma, which is a small number, and you find the s which satisfies that equation. There are well worked out formulae for doing all these things. So calculation is not the problem, just the comprehension. Similarly, if you have n counts and with a known background b, then you do the same thing. It's rather than showing you all these formulae, maybe I should just show you some plots of what it looks like. So here, for instance, are confidence intervals for a defined background. By the way, another item of jargon with statisticians is that they use lambda as a thing that denotes intensity. It is not really wavelength. So this took us, I think, two years to figure out what was going on during our collaborations. Really seriously, I mean, for us it is hard-coded that lambda is wavelength, and for them it's hard-coded that lambda is intensity. So for different values of the background, and suppose you observe different numbers of counts, that is what these plots are showing. And the width of these boxes tells you what the confidence interval is, And the height of these boxes tells you what is the probability of actually seeing that many counts given the true value, which is this dashed line. Okay. Just to zoom in here, just to show you some problems. So here, for instance, this is the case for a background of 3 counts. 3 counts in an area of 10 times the source counts. And then the source is at 5 counts, let's say, and then you expect to see these many. If you see these many different observations, then these are the intervals that are calculated for those things. You'll notice that for the extreme cases, the intervals actually do not cover the true value. And that is okay, because the probability of seeing these such large counts is actually very small. And these things are called empty intervals, and these are, they as long as the fraction in which it does cover is correct, then it does. Nobody cares what happens in the extremes. These are, by the way, 95% intervals. Eric, this is your slide. Eric asked me to put this in. In 1998, 2 people, Feldman from Harvard, actually, and Cousins, I don't know where he's from, came up with a way to do this, to avoid this problem of the empty intervals for the Poisson case. And what they decided, their prescription was quite simple. Now, instead of just taking the likelihood, take the ratio of the likelihood to the likelihood for the most probable value. What that simply does is that it kind of shifts those intervals that I showed before, and just essentially renormalizes the thing and produces unified intervals where the lower bound automatically drops to 0 for small n, and it's very generally well behaved. Okay. I want you to remember this, because this is going to matter when we come to the upper limits part. Because this, in the physics literature, these bounds of these intervals are called upper limits, and that can lead to considerable confusion if depending on what you're trying to talk about. So, aperture photometry. So generally, you see these big images with large number of photons, and then there's a big source, and then usually the way you estimate things is you put a big circle around the source, you collect all the counts, and then you put a big annulus somewhere off the source, and you collect all the counts there, and you say that's the background. So you have measured counts C in the circle, B in this annulus. And what you want to do is infer the expected counts from the source and the background. And what you know is this, that the C is derived is as a Poisson, actually there should be a tilde, okay. It's a Poisson sampling of the sum of theta S and theta B, where theta B is the intensity of the background under the source. And then the background counts are Poisson of R, which is the ratio of the areas between between the yellow circle and the red annulus, times the same theta. You're just translating it up to a different area. So, what do you do with that? Just to remind you, so this is the Poisson likelihood, the Bayes theorem, the gamma distribution, and the statistical model that you're using. And what you do now is you take each of these things that you want to figure out, the theta S and the theta B, and then you derive, you apply Bayes theorem and the Poisson likelihood to it. So first of all, the 2 parameters, we can write down the gamma prior for that. We can set alpha S to be 1 if you want to, and beta S to be 0 if you want it to be non-informative. And but I would recommend that we do that at the end of the analysis, not right now. because if you do that, this becomes an improper prior. And then you can write the likelihoods for both the background and the counts, for the source counts. And you write it down exactly as the Poisson likelihood over there. And now you consider the joint distribution, and then you apply Bayes' theorem. So to make the likelihood function and the two priors, you can break this down into again applying the Bayes' theorem. Notice that I'm completely dropping out the denominator because it's just a normalization factor. Everything integrates to 1. And then you can marginalize out the theta b, which is the background intensity, which you are not interested in, simply by integrating out of that. I am not going to walk you through the entire calculation. Do I hear a hallelujah? But I'm just going to leave you with the final answer expression. And as I said, look in Frank's paper to see what happens if you make other complications. This is numerically evaluatable, I suppose. Even though it's not quite as simple as S minus B as you would expect. And here's what the posterior distributions look like for different cases. So, for instance, you have the upper plot is for a background of 5 counts, and the lower plot is for a background estimate of half counts. The yellow curve is the Poisson posterior distribution, and the green curve is the Gaussian approximation. You just take source minus background and you subtract the thing and see what you get. Notice, by the way, that this is the 0 line, and what is happening here is that we are just changing the when the source is of different values, what happens. The Gaussian, of course, has no trouble going below 0; it just keeps going. Whereas the Poisson distribution, just kind of bumps up against 0 and is well behaved. So it's always guaranteed to give you good results, even in the low counts limit. Okay.
Can you go back to the equations? Did your prior drop out?
It is. Oh, I'm sorry. I should have said. Thank you. Yes, this is the. I should have mentioned that. This is for the case when alpha. I took the non-informative prior. You're right. Yes, okay. The prior did. It's took the limit to that value, so it dropped out. Right. Come back. And this is also calculated for the same non-informative prior. Okay. So finally, on to upper limits. So we talked about confidence intervals or credible ranges, and they give a range of values that a parameter can have for a specified significance, right? And they give an interval, and the interval has 2 ends, a lower bound and an upper bound, right? And the true value, by definition, is likely higher than the lower bound and lower than the upper bound. So the question that that comes up and has been coming up for the past 20 years, since after the Isobe, Feigelson, and Nelson, actually, Eric, is that why is this not an upper limit? You have it, you have a parameter value, it is less than something, and why is that something not the upper limit? And the reason is that think about when you use upper limits, right? It is when you make an observation, you expect to see something, but you don't, and you want to know how bright the thing was, or should have been, or was not, that you did not see. Which means that there is the question that you're actually asking yourself is this: what is the largest intensity? Something happened to this. What is the largest intensity that a source can have without being detected? Or what is the smallest intensity that a source should have in order to be detected. So, astronomers generally tend to define an upper limit in the context of a detection. If something is detected when some measurable statistic, something goes above a preset threshold, then, and usually that is the way we work with detections. There may be other ways to do this that are coming up, but at least as for now, something is detected when you can say that it is not part of the background. So for a simple thing, for example, is you can have test statistics just as a number of observed counts, and you set the threshold as at 5 counts. So if anything that is, if more than 5 counts are seen, you claim a detection. And if fewer are seen, then the source must be less bright than some value, right? Because you haven't seen it; it's not been detected, and that is what we tend to call the upper limit, right? So the fact that you're talking about a something that is beyond the background, that's the threshold above the background, and something that is related to how bright the source could be, that means that we need both type 1 and type 2 errors to define this concept. Eric mentioned on Wednesday, how you got to be very precise in asking statisticians when you have a question to them, and I think in a large number of cases, recently at least, astronomers and physicists have been asking them the wrong question, and and getting back what the statisticians think is the right answer, which is here you have the bounds and use those. Whereas what we really need to do is to define it in the context of the detection.
Excuse me.
Yeah.
Sorry, a question about that last slide. I might have missed it when you said it before. What are type 1 and type 2 errors?
I'll mention that in a moment. So type 1 errors are actually the false positive probability, and type 2 errors are the false negative probability. So you generally, the way we do detection is we have a background, and then we ask what is the significance at which you're going to accept background fluctuation above a certain value. So if you think that there are you're willing to accept fluctuations larger than 3 sigma as being not due to the background, then any 3 sigma fluctuation that you see must be the source. So that is basic. So that 3 sigma quantity that defines the type 1 error. Similarly, you have a source that might be sitting close to this threshold, and if that is the true value of the source intensity, sometimes it will produce fewer counts, sometimes it will produce more counts, and half the time it won't be detected. And that is the false negative. There's something that exists, but you don't see it. That is the type 2 error. So that's basically what I would say here. So the upper limit then is such that the probability that the test statistics is greater than the threshold defined for the type 1 error, and that probability should be greater than or equal to the type 2. And this is a graphical explanation of the same thing. This thing, really can't see anything here. This curve up here is let's say the distribution of the background, and you set a threshold here at some point, and you expect a very small value of the background to exceed that. And if you do see this in the observation, you call it a source. This is what you're willing to accept in a background as the false positives. Now you might have a source that sits here, and depending on where the true value is, it could be like that, or it could be like that, and there is some fraction of the time that it falls below this threshold, and it will not be detected, and that's the type 2 error. So and then you, depending on what you choose your beta to be, that is how you set your upper limit. So the point is that there are 2 things you got to specify in order to say what the upper limit is, and that is the type 1 error probability alpha and the type 2 error probability beta. So these are curves that are calculated for different values of the source intensity for beta as a function of the source intensity for different values of the background. And then you pick a certain value of the alpha that you're willing to willing to accept, and then you go off and read what the upper limit should be. This is another plot that's very similar, which I'm going to, since I already, we'll come back to this if we need. But generally, what you really have to notice is that you should calculate beta curves for different values of the source intensity, and then you choose whatever value that you're going to use, and then you read off the intercept, and that tells you what the upper limit should be. Just a zoomed in version of that for if you want to see more clearly. So some of the properties that as defined for these upper limits is that it depends on the detection process. For instance, if you're using wave detect, it's going to give you a different upper limit than cell detect. It does not depend on the number of counts that you observe in the source region. It does depend on the background and the exposure. So this is something that's something that you can say what the limit should be before you're done a source measurement, which is as it should be, which is the way that at least that I think that most astronomers think of it as. But if you do make a measurement of the source intensity, then what you get are upper bounds on the source intensity, right? It's not quite. It has nothing to do with detection. You can get an upper bound on the source intensity for anything. So the basic recipe is this. So you define a test statistic for measuring the strength of a source signal. You set the maximum probability for a false detection, alpha. It's usually 0.003 for astronomers, 3 sigma. Even though we shouldn't be doing it, we should have to. Wave detect, for instance, uses 1 over the number of the pixels that are active. And you compute the corresponding detection threshold. And then you compute the probability of the detection for that threshold. And then you define the minimum probability of detection. One simple thing that you can do is choose beta of half. That means that when you have an upper limit, it is going to be sitting right on the threshold. You could choose beta of 0.9 if you want to be very conservative. And then you compute the upper limit as that value of theta such that beta is greater than beta, that minimum that you chose. So that's all I have. I have some things for further reading, including a very nice paper from 1986. And if you have any questions. Okay. Now is the time to wake up. Yeah?
How would you insert these upper limits into your Bayes theorem? Would you truncate the function that you're working with based on the observed probability?
Brilliant question. The question is, how would you use these calculated upper limits in any further? How do you propagate this further? Typically, what people used to do was simply say that there is one upper limit and say that there is everything below that is plausible. That is the foundation of survival analysis that Eric has in ACER, I believe. And clearly, you can do better. And the fact that you have these curves, right? So when you have a probability model for for how you estimate the posterior probability distribution for a given background and a source, you can make you have access to this function. So for a given beta, you know exactly what that looks like, and in principle, you can use this downward trend that you see here, right? That is exactly what you would expect to see for a undetected source if it were right at the threshold. That is one thing you can do. This has not been. There's no theorem or anything that we have worked out yet to figure out what it should be. In principle, I suppose you would include some information about the log and log S distribution of the sources, because there are going to be more weak sources than there are faint sources, and you have to include that in some fashion. There is a paper by Fabrizia Guglielmetti, I believe, who used this kind of log and log S information to estimate as a prior information. So yeah, there are ways to do it, different ways to do it, and there is no definitive answer yet. But very good question. So, Eric?
I'll ask this question in two ways. Since the scientist is now specifying two parameters, alpha, two probabilities, alpha and beta for type 1 and type 2 errors, is this an implementation of Benjamini and Hochberg's false discovery rates philosophy for multiple hypothesis testing? But in your case, it's not multiple.
Right.
It sounds to me it's closely related. Is that true?
I don't know if it is closely related. You're right. The false discovery rate is not just the same as the type 1 error. Quite honestly, I am not familiar enough with that to know to explain this. But there's a.
It seems to be philosophically similar, but
could be. Yeah.
You clearly have a Poisson problem, and you're addressing a specific problem, and it's not multiple hypotheses.
It is not multiple.
So, but it seems to have a relationship. Maybe we should ask David sometime.
Yeah, false discovery rates are curious things, right? I mean, it depends on, as you said, how many detections or how many false positives that you expect to see and everything. So there could be some connection there. But, I think, I don't want to say things that I might be completely wrong about. So it's something that I need to check out.
I don't
right?
know either.
We do, indeed. Right. Okay. Thank you. So we can take a 5-minute. Sure. Let's take a 5 or actually 10 minutes break.
Okay.
We'll start at 2:30.
At 2:30 exactly. Very good. 10-minute break.
10 minutes. 9 minutes.